So this is number theory, lecture 9. We're going to start to talk today about congruences in chapter 2, but there were some questions about homework. So in section 1.5, number 1, the problem is to use the sieve Eratosthenes, the sieve of Eratosthenes, to find all the prime numbers up to 210. So first thing you do is, what is the square root of 210? So we don't need to know exactly, but the square root of 210 is what? Well, 14 squared is 196. 15 squared is 225. So the square root of 210 is between 14 and 15. And the principle of the sieve of Eratosthenes says that every prime number p less than or equal to 210, every composite number the number is composite and no bigger than 200, so every composite number n less than or equal to 210 is divisible by a prime that's less than or equal to the square root of 210, which means less than or equal to 14. Right? So this is the fundamental principle behind the sieve of Eratosthenes. If a number is composite, that means it's a product of two integers, and one of them is going to be less than or equal to the square root of the number. So if n is a number up to 210 and it's composite, then it's divisible by a prime less than or equal to the square root of 210. The largest integer less than or equal to root 210 is 14. And what are the primes less than or equal to 14? That means n is divisible by one of the primes 2, 3, 5, 7, 11, or 13. These are all the primes less than or equal to 14. So to find all the primes less than or all the composite, to find all the numbers less than or equal to 210, you literally write down every number up to 210. That takes 2 or 3 minutes. All right, 1 you can cross out. Then the first number you see is 2. 2 is a prime, but then you cross out all the multiples of 2. The next number, up to 210. The next number you see is 3. That's a prime, but then you cross out all the multiples of 3. And you do that for all 6 of these primes, 2, 3, 5, 7, 11, 13. When you've crossed out all the multiples of these numbers up to 210, the numbers that are left are the primes. So that's the sieve of Eratosthenes. And if you look at the examples just before the exercises, where I use the sieve of Eratosthenes to find all the prime numbers up to 60, you see exactly what's going on. If you look at the book on page 34, just before the exercises, there's all the numbers up to 60. In the next chart, I've crossed off 1 and all the multiples of 2, starting with 4, then all the multiples of 3, starting with 6, and so forth. And when I'm done, I've crossed out every composite number up to 60, and the numbers not crossed out are the primes. Right?
Professor?
Yeah.
it says what compute pi 210.
Right.
Is that the same thing as less square root 210?
No. So again, you have to be reading the book. At the beginning of section 1.5, it defines
Oh, okay.
pi of x is the number of primes
Okay.
less than or equal to x. So pi of 210 is the number of primes up to 210. And the way you calculate that is you use the sieve of Eratosthenes. You cross out you find all the primes up to 210, and then you count how many there are.
Okay.
Any other questions about this? Sieve of Eratosthenes is really very important historically and in practice. Right. I think someone asked about problem 13 in section 1.4. So section 1.4, exercise 13, concerns the number, the function Vp of n. So you fix a prime number p, and the function for every integer n, Vp of n is k if p to the k divides n and p to the k plus 1 does not divide n. So k is the largest power of the prime p that divides n. So by the fundamental theorem of arithmetic, every n is a product of primes, p1 to the v1, p2 to the v2, let's say p sub r to the v sub r, and these exponents give you the highest power of each of these primes that divides n. So this is the definition of this function, right? So that's what you need to think about and understand. That really is the crux of this. So for example, so if Vp of a number m is equal to k, and Vp of n, a number n, is equal to L, then what does that mean? It means that m is p to the k times some number m1, and n is p to the L times some number n1, where p does not divide m1 or n1. That is, when you factor m, or write m as a product of primes, p to the k is the power of the prime p that occurs in m. So m is p to the k times m1. Similarly, n is p to the L times n1, and p doesn't divide m1 or n1. But then what is m times n? M times n is p to the k m1, p to the L n1, p to the k times p to the L is p to the k plus L times m1 n1, m1 times n1. And if p doesn't divide m1 or n1, p does not divide m1 times n1. So the highest power of p that divides mn is k plus L. So Vp of mn is k plus L, which is k is Vp of m, and L is Vp of n. Okay. That's what you were asked to prove. And is there a question about this? Can I explain this further? I'll just give an example. Suppose I take M to be 108 and N to be 42. So, and I take P to be 3. So M, which is 108, is, I think this is 27 times 4. It's 3 cubed times 4. And N, which is 42, is 3 times 14. 3 to the first power times 14. So V3 of M, V3 of 108, is 3. V3 of 42 is 1, right? 1 is the highest power of 3 divides 42. 3 is the highest power of 3 that divides 108. And if I multiply these two numbers, V3 of 108 times 42 would be 3 plus 1, or 4.
Okay, hello, Professor.
Yeah,
How come, can you push the paper a little up? I can't read the bottom. Is there any way you can help?
that's all there is. Let me write it on another piece of paper, maybe bigger for you. So suppose I take the prime P equal 3, and I take the number M to be 108, and the number N to be 42. So I want to know the power of 3 that divides each of these numbers. So 108 is 27 times 4. That's 3 cubed times 4. 42 is 3 times 14. So the highest power of 3 that divides 108 is the third power. The highest power of 3 that divides 42 is the first power. What about 108 times 42? So that's 3 cubed times 4 times 3 times 14. 3 cubed times 3 is 3 to the 4th. 4 times 14 is 56. That's not divisible by 3. So V3 of 108 times 42, the highest power of 3 dividing this number is the fourth power, which is 3 plus 1. 3 was V3 of 108, and 1 is V3 of 42. Right, so this is just an example of what is being given in the exercise. Okay. Any questions about this?
Can I see the other paper, please?
Okay. All right. So now we start chapter 2 on what are called congruences. This is another of the absolutely fundamental notions in number theory. And we fix a positive integer m. Let m be a positive integer. And the number m that you pick is sometimes called the modulus. And let a and b be any integers. So we say that, so this is the definition, which is fundamental. A is congruent to B modulo M if M divides the difference A minus B. So for example, if I take M equal to 5, A equal to 31, and B equal to 76, A minus B is 31 minus 76. I think that's equal to minus 45. Minus 45 is 5 times minus 9. So 5 divides the difference, A minus B. So 31 and 76 are congruent modulo 5. And the notation that we use, A congruent to B mod M, is A, 3 lines, B, in parentheses, mod M. So this is the notation. This means that A congruent to B mod M, M divides the difference, A minus B. So this just shows that 31 is congruent to 76 mod 5. Okay. Any two even numbers are congruent mod 2. So for example, 72 is congruent to 44 mod 2 because 2 divides 72 minus 44, which is 28. 28 is 2 times 14. 73 is congruent to 45 mod 2. Any two odd numbers are congruent mod 2 because 2 divides 73 minus 45, which is also equal to 28. So this definition of congruence, you must know. Memorize it. We use it all the time. You have to memorize it. You have to know exactly what congruence means. So we can ask a question, take two numbers at random, 79 and 41. Are these numbers congruent mod 2 or mod 3 or mod 4 or mod 5? Or mod 19? Any numbers you like. These are questions for which there's a yes or no answer. So let's see, 79 minus 41 is 38. That's 2 times 19. So 79 is congruent to 41 mod 2. because 2 divides the difference. 79 is also congruent to 41 mod 19, because 19 divides the difference. 79 is not congruent to 41 mod 3, because 3 does not divide, that's what this symbol means. 3 does not divide 38. And 79 is not congruent to 41 mod 5, because 5 does not divide 38. Right? So a pair of numbers can be congruent with respect to different moduli and not congruent with respect to other moduli. Right? So this is really one of the most fundamental definitions, one of the most fundamental concepts in number theory. So any question about the definition?
Professor, what's mod? What's the mod? Can you go back to the other page?
So this is the definition. A is congruent to B modulo M. And the notation is A, and then these 3 bars, 3 horizontal lines, B, in parentheses mod M. That's the notation. And that means that M divides A minus B, right? If M divides the difference of A and B, then we say A is congruent to B mod M. So 31 is congruent to 76 mod 5, because the difference is minus 45, which is a multiple of 5.
Can I see the other page? Is that 79 equals 41 mod 2? Is that mod 2 or what?
This is not equal. This is, you read this as congruent.
Congruent.
79 congruent to 41 mod 2,
Okay.
because the difference is divisible by 2.
Okay.
The difference of those 2 numbers is 38. And then the relation of congruence satisfies the following 3 properties. The first property is called reflexive. Every number is congruent to itself mod M, because what is the difference? A minus A is 0, and 0 is divisible by every number. So the first property of congruence is reflexivity. Every number is congruent to itself mod M for all A and M. There's also symmetry. If A is congruent to B mod M, then B is congruent to A mod M. And the reason is very simple. If A is congruent to B mod M, this implies A minus B is a multiple of M times Q for some integer Q, which means if you multiply by minus 1, B minus A is M times minus Q. If M divides A minus B, then M divides B minus A, which means B is congruent to A mod M. So congruence is reflexive, it's symmetric, and it's also transitive. So that means that if A is congruent to B mod M, and B is congruent to C mod M, then A is congruent to C mod M. So if A is congruent to B and B is congruent to C, then A is congruent to C. And what is the reason for that? If A is congruent to B mod M, that means A minus B is M times Q. If B is congruent to C mod M, that means B minus C is M times some number Q prime. If I add these two equations, A minus B plus B minus C, the B's cancel. I get A minus C is MQ plus MQ prime, which is M times Q plus Q prime. So M divides A minus C. So A is congruent to C mod M. So these are basic properties of congruence, which allows us to do a lot of nice arithmetic. Okay. So you have to know the definitions of the words reflexive, symmetric, and transitive. A relation is reflexive if every element A is related to itself. Here the relation is congruence modulo M. Every number A is congruent to itself mod M. It's symmetric. If A is related to B, then B is related to A. In this case, that means if A is congruent to B mod M, then B is congruent to A mod M. And it's transitive. Transitive means if A is related to B and B is related to C, then A is related to C. In this case, this means if A is congruent to B mod M and B is congruent to C mod M, then A is congruent to C mod M.
Is that symmetry or
Is what symmetry?
number two?
Yes, symmetry.
Oh.
Again, it's all in the book, and the book is on Blackboard. So the way you learn this is by studying the book. The lecture notes are just explaining the book, but the primary source for everything we do is the textbook. That's what you have to know. Okay. So related to this definition of congruence are what are called congruence classes. So again, M is a fixed positive integer, the modulus. What is called the congruence class of A, lowercase a, of A modulo M is the set of all numbers B such that A is congruent to B mod M. So for example, the congruence class of 0 modulo 2 is the set of all numbers B such that 0 is congruent to B mod 2. Let me actually write it. A congruent to B is the same as B congruent to A. So it's all numbers B such that B is congruent to 0 mod 2. What is B congruent to 0 mod 2? This is all numbers B such that 2 divides B. B minus 0 is B, 2 divides B. What do we call the numbers divisible by 2? The even numbers. So this congruence class of 0 mod 2 is the set of all the even numbers. Right? 0 plus minus 2 plus minus 4 plus minus 6 and so forth. This is our first example of a congruence class. What is the congruence class of the number 1 modulo 2? It's all numbers B such that B is congruent to 1 mod 2. This means the set of all numbers B such that B minus 1 is divisible by 2, is 2q for some integer q. So this is a set of all numbers B such that B can be written in the form 2q plus 1. What are the numbers 2q plus 1? These are the odd numbers. So the congruence class of 1 modulo 2 is this infinite set of all odd numbers.
The professor?
Yes.
Oh, sorry, yeah. I said a quick question. See, on the homework, do you grade all the problems or just some?
I certainly don't grade all the problems. What I really do is look and see that you've made a reasonable effort to solve at least most of the problems in the homework set. And if you've done that, you get the full number of points, which is 2 points for the homework.
Okay.
Right? But
Okay.
it doesn't mean that you've solved the problems correctly. If you have a question about how to do an exercise, you need to ask me either in class or in one of the problem sessions.
Okay. Okay. All right, thank you.
What is the congruence class of 0 mod 3? It's the set of all numbers. Well, let me just write n. So I've said n is congruent to 0 mod 3. This is all numbers n such that 3 divides n minus 0 or n. So this is the set of all multiples of 3. Right? That's the congruence class of 0 mod 3. What's the congruence class of 1 mod 3? That's all numbers n such that n is congruent to 1 mod 3. That's all numbers n such that 3 divides n minus 1. That's all numbers n such that n minus 1 is some multiple of 3, which is all numbers n, which you can write as 3q plus 1. That is, all numbers that leave a remainder of 1 when you divide by 3. So we have 1, 4, 7, 10, 13, and so forth. And negative numbers, -2, -5, -8, and so on forever, right? This is the congruence class of 1 mod 3. What's the congruence class of 16 mod 3? It's all numbers n, such that n is congruent to 16 mod 3.
Professor, I'm
Yeah.
confused. Why did you use n-1 over here?
Here? Because I'm trying to find the
Yeah.
congruence class of 1 mod 3. So I'm given the 1 and I'm given the 3. This is all numbers n. This is the definition of a congruence class. All numbers congruent to 1 mod 3. That's what this says. All n such that n is congruent to 1 mod 3. Right? That's the problem. The congruence class of 1 mod 3, so that's why I have 1 mod 3 here. This
And
means,
the n-1 right here. 3 divides n-1?
so what is this? What is the definition of this? N is congruent to 1 mod 3 means 3 divides the difference of these two numbers. 3 divides n-1. That's the definition of congruence.
Okay.
Right? So 3 divides n-1 means n-1 is 3 times some number q. So n is the number of the form 3q plus 1. And what are the numbers of the form 3q plus 1? 1, 4, 7, 10, 13, and so on forever, going to plus infinity, and -2, -5, -8, and so forth, going to minus infinity.
Okay.
What is the congruence class of 16 mod 3? It's all numbers such that n is congruent to 16 mod 3. Now you can find that easily if you observe that 16 is congruent to 1 mod 3, because 3 divides 15, which is 16 minus 1. So if n is congruent to 16 and 16 is congruent to 1, by transitivity, this is all n congruent to 1 mod 3. Which is exactly this set we found a moment ago.
We can't see the screen. It's like, it's not clear. It's blue.
Yeah, I don't know what's going on here. Suddenly it turned blue, so I don't know. And it's so I don't know whether something is going on with my camera.
Now it's purple.
Well,
Okay.
yeah, I have no idea what's happening there. But again, everything is written down in the textbook, so that's the fundamental resource.
Well, Professor,
Yes,
what does that side say? 16 is congruent to 1 mod 3, because 3 divides 15 times 16, was that?
No, 15,
Yeah.
which is equal
All equal, okay. Yeah?
16 minus 1,
Oh, 6, okay, okay.
right? 16 minus 1 is 15.
Okay.
What's that 3Q plus 1? What is that for? What's the Q?
Sorry?
Q. What's the
Over
Q
here?
stand for? Yeah.
Well, to say 3 divides n minus 1 means that n minus 1 is 3 times some number. I'm calling that number q. This means that n minus 1 is 3 times q for some integer q.
Okay.
That's what divisibility means. 3 divides a number means the number is 3 times something, q. So n minus 1, if you divide it by 3, you get a quotient q, and the remainder is 0. And if n minus 1 is 3q, bring the 1 to the other side, n is 3q plus 1. So this is the notion of a congruence class.
Let me finish writing that.
Okay. Now, remember the division algorithm, long division. If you take any number n and divide it by m, you get m times a quotient plus a remainder, where the remainder is some number between 0 and m minus 1. That's the division algorithm. So if n equals mq plus r, then n is congruent to r mod m. And minus r is the multiple of m. So every integer, every number belongs to a congruence class of the form all n congruent to r mod m for some r, that's my remainder, between 0 and m minus 1. And not only does it belong to a congruence class, it belongs to a unique congruence class. Plus, there's exactly one number between 0 and m minus 1, such that n is congruent to that number, mod m. And we denote this congruence class by r plus mz. So r plus mz is the set of all numbers congruent to r mod mz. So for example, if m equals 2, every number is 2q plus a remainder, where r is 0 or 1. R is 0 if the number is even, and r is 1 if the number is odd. So if we look at 0 plus 2z, which we just write as 2z, This is all numbers n congruent to 0 mod 2. 1 plus 2z is all numbers n such that n is congruent to 1 mod 2. This is the even numbers, and these are the odds, the set of odd numbers. And if we take the whole set of all integers, it's the union of 2z and 1 plus 2z. It says all we're saying is if you take the integers, you can divide it into two classes, the numbers that are even, the numbers that are odd. The numbers that are even are in the congruence class 2z. The numbers that are odd are in the congruence class 1 plus 2z.
Professor,
Yeah.
is there any way you can push the paper down? I didn't get the top portion. I think it was a definition. Yeah, that one. Yeah, okay. I'll give you division algorithm.
So it's not a definition, it's just
Oh.
this is the division algorithm. Every number, if you divide it by m, it gives you a unique quotient and remainder, and the remainder is between 0 and m minus 1. And if n is mq plus r, then n minus r is m times q, which means n is congruent to r mod m. So every number is congruent to its remainder when you divide by m. And that means every number, every integer, is in a unique congruence class, n congruent to r mod m, for some r between 0 and m minus 1. And the notation for this congruence class is r plus mz. R plus mz is the set of all integers congruent to r mod m. If I take m equal 2, there are only two remainders, 0 or 1. The numbers congruent to 0 mod 2 are the evens, the numbers congruent to 1 mod 2 are the odds, and the set of integers is partitioned into two sets, the even numbers and the odd numbers, those two congruence classes. If I take modulus m equal to 3, the congruence class 3z, it's all n congruent to 0 mod 3. It's all numbers of the form 3q, where q runs through all the integers. It's all the multiples of 3. 1 plus 3z is all n congruent to 1 mod 3. That's all numbers of the form n equal to 3q plus 1. So this is a set 0, plus minus 3, plus minus 6, and so forth. This is a set 1, 4, 7, minus 2, minus 5. 2 plus 3z, it's all numbers congruent to 2 mod 3. This is all numbers n that you can write as 3q plus 2 for any integer q. So that's 2, 5, 8, minus 1, minus 4, and so on. And if we take the set of all integers, z, it's divided into three classes, three congruence classes, 3z, 1 plus 3z, and 2 plus 3z. Every number leaves a remainder of 0, 1, or 2 when you divide by 3, and that determines these three classes. let's step back for a second and just give you a chance to practice something. So find all positive integers that say n less than or equal to 50, such that n is congruent to 3 mod 7. Right. So find all the numbers between 1 and 50 that are congruent to 3 mod 7. So what's the answer? What's the smallest number up to 50 that's congruent to 3 mod 7? Is 0 congruent to 3 mod 7?
Mhm.
Is 20 congruent to 3 mod 7? Is 50 congruent to 3 mod 7? What are the numbers congruent to 3 mod 7? Well, of course, 3 is, because every number is congruent to itself. So 3 is certainly congruent to 3 mod 7. But if a number is congruent to 3 mod 7, that means n minus 3 is 7 times q, or n is equal to 7q plus 3. So I can make a table for different values of q. Here I put 7q plus 3. When q is 0, I get 3. What do I get when q is 1? When
10.
q is 1, what do I get?
10,
10. What do I get when q is 2?
14, 17,
When q is 3?
24.
When q is 4?
Mm.
31.
51,
When q is 5? 35 plus 3 is 38.
38,
When q is 6, 42 plus 3 is 45.
45,
When q is 7, 49 plus 3 is 52. That's too big because I'm only going up to 50. So the answer is the set of numbers 3, 10, 17, 24, 31, 38, and 45. Each of these numbers, if I subtract 3, is divisible by 7. So that's the set of numbers up to 50 congruent to 3 mod 7. Any question about how I got this? Let's try
Wait,
another problem
1
of this
second.
sort.
Wait 1 second. Okay.
Find all n such that n is positive between 1 and 50, And n is congruent to 11 mod 8. What numbers are congruent to 11 mod 8? Let's see. N is congruent to 11 mod 8 means n minus 11 is some multiple of 8 for some integer q, which means n is equal to 8q plus 11 for some q. So I could take, again, I could make a little table. Let's just take some values of q, 0, 1, 2, 3, and 8q plus 11. When q is 0, I get 11. When q is 1, I get 19. When q is 2, I get 16 plus 11 is 27. When q is 3, 24 plus 11 is 35. When q is 4, 32 plus 11 is 43. When q is 5, 40 plus 11 is 51. That's too big. So these numbers certainly satisfy it. But in fact, that's not all, because there's no reason to restrict q to being positive. If q is minus 1, minus 8 plus 11 is 3. So that's also good. So the answer is the set 3, 11, 19, 27, 35, 43. That's the set of integers, of positive integers up to 50 that are congruent to 11 mod 8. Now, congruence, are any
Professor, why
questions
you
about this?
included 3 in the answer? Why you included 3?
Well, is 3 between 1 and 50?
Yeah.
Is 3 congruent to 11 mod 8? Three minus 11 is minus 8. That's 8 times minus 1. So
Okay.
3 minus 11 is divisible by 8.
Okay.
Okay. So with ordinary numbers, integers, we can add and subtract them. We can multiply them, still get integers. You can't necessarily divide an integer by another integer and get an integer, but You can add, subtract, and multiply. And something similar is true for congruences. So suppose we fix a modulus m, A1 is congruent to A2 mod m, and B1 is congruent to B2 mod m. So suppose we have numbers A1, A2 that are congruent mod m, and numbers B1 and B2 that are congruent mod m. This means that A1 minus A2 is m times some quotient q. And this means B1 minus B2 is m times some quotient q prime. If I add these two equations, I get A1 plus B1 minus A2 plus B2 equals MQ plus MQ prime, which is m times q plus q prime. So this number minus this number is divisible by m. So A1 plus B1 is congruent to A2 plus B2 mod m. Right? If A1 is congruent, the modulus doesn't change, that's fixed. If A1 is congruent to A2 and B1 is congruent to B2, then we can add the congruences. And this is what we get. And similarly, from these two equations, A1 minus A2 equals MQ, B1 minus B2 equals MQ prime. If I subtract, I get A1 minus B1 minus A2 plus B2, which is minus A2 minus B2, is m times q minus q prime. So I can subtract congruences. If A1 is congruent to A2 and B1 is congruent to B2, then A1 minus B1 is congruent to A2 minus B2 mod m. And not only that, you can also multiply congruences. So if A1 is congruent to A2 mod m, this means that A1 minus A2 is MQ, or A1 is A2 plus m times q for some q. And if B1 is congruent to B2 mod m, this means B1 is B2 plus MQ prime for some q. So what happens if I multiply A1 times B1? That's A2 plus MQ, B2 plus MQ prime. So let me multiply this, right? I know how to multiply A2 B2 plus M A2Q prime plus M B2Q plus M squared QQ prime. And from this part, I can factor out an M. A1 B1 equals A2 B2 plus M times the quantity A2Q prime plus B2Q plus MQ Q prime. Which means M divides the difference of these two numbers. So A1 B1 is congruent to A2 B2 mod M. So this is really important. If you have congruences, A1 congruent to A2 and B1 congruent to B2, you can add the congruences, you can subtract the congruences, and you can multiply the congruences. Okay. So let me just give a numerical example of this. We have, let's say, 29 is congruent to 16 mod 13. And 11 is congruent to minus 2 mod 13, right? Because 29 minus 16 is 13, and 11 minus 2 is also 13. If I add these congruences, I get 40 is congruent to 14 mod 13. Is that correct? Well, 40 minus 14 is 26, which is 13 times 2. So that's correct. Suppose I subtract the congruences. 29 minus 11 is 18. 16 minus 2 is 18. And 18 is congruent to 18. 18 minus 18 is 0, which is 13 times 0. So I can subtract. Can I multiply the congruences? Let's see, what is 29 times 11? $319. What is 16 times minus 2? Minus 32. Is 319 congruent to minus 32 mod 13? Let's check. 319 minus 32 is 319 plus 32 is 351. Is this divisible by 13? Let's see. 13 into 351 goes twice, 26, 91, 7. This is 13 times 27. So this is also correct. So we have this pair of congruences. I can add them correctly. I can subtract them correctly. And I get a correct congruence also if I multiply them. You can't divide because you would get fractions, and fractions don't enter into congruences. Any questions about this? Now, we can interpret this in the language of congruence classes. So in the language of congruence classes, what does this mean? Suppose we have the congruence class A plus MZ and the congruence class B plus MZ. So suppose A1 and A2 are in the congruence class A plus MZ, and B1 and B2 are in the congruence class B plus MZ. So actually, I'm not even sure I need the A2. So A1 is congruent to A mod M, and B1 is congruent to B mod M, which means A1 plus B1, I'm adding these congruence classes, is congruent to A plus B mod M. I don't need an A2 here, that's unnecessary. Just A1 is in the congruence class A plus MZ. B1's in the congruence class B sum plus MZ. So A1 plus B1 is A plus B MZ. So A1 plus B1 is in the congruence class A plus B plus MZ. So no matter what element I choose from the congruence class A plus MZ, and what element I choose from the congruence class B plus MZ, when I add those two elements, I get something in A plus B plus MZ. So I can define addition of congruence classes. I define, if I have A plus B MZ and B plus MZ, I can define the sum to be A plus B plus MZ. And this is well defined. If I take any number here and any number here and add them, I get a number in here. And by exactly the same argument, I can subtract congruence classes. I have the congruence class A plus MZ and B plus MZ. If I subtract them, I can define that to be the congruence class A minus B plus MZ. And I can multiply them. Just by multiplying these numbers A, B. So I can define addition, subtraction, and multiplication of congruence classes. And the upshot of this, the consequences of all this, is that Z mod MZ is what is called a ring in algebra. Namely, it's something where you can add, subtract, and multiply, and all the usual rules of arithmetic satisfied. So Z mod MZ, what is this? This is the set of all congruence classes A plus MZ. So this is a finite set. It consists of M congruence classes, and that's a ring with addition defined by just adding the A and B, and multiplication defined by just multiplying the A and B. So again, the simplest example is always the case M equal 2. Z mod 2Z consists of the two congruence classes, 2Z and 1 plus 2Z. This is the set of even numbers. This is the set of odd numbers. And what is the addition table? 2Z, 1 plus 2Z, 2Z, 1 plus 2Z. This is 0 plus 2Z, 0 plus 2Z, 0 plus 0 is 0. You add these two, you get 2Z. 2Z and 1 plus 2Z is 1 plus 2Z. 1 plus 2Z plus 2Z is 1 plus 2Z. And 1 plus 2Z times 1 plus 2Z is 2 plus 2Z, which is the same as 2Z. And this is just a way of writing what they teach you in elementary school. The sum of two even numbers is even. The sum of two odd numbers is even. But an even plus an odd number is odd. And what about the multiplication table? Zero times 0 is 0. 0 times 1 is 0. 1 times 0 is 0, and 1 times 1 is 1. And again, this is just what more of what they taught you in elementary school. The product of two even numbers is even, and even times an odd number is even, but the product of two odd numbers is odd. So this is elementary arithmetic written in the language of congruence classes. Okay. So everything we've done is in chapter 2, section 2.1. And my advice is to study this material. It's very, very important. A large part of what we do, everything that we do, in fact, in this course from now on, involves congruences. So they're introduced in section 2.1, and you really need to put in a lot of time to master the concepts. Any questions about any of this? There is a lot to learn here, and there's no way to do anything other than to put in a lot of time. Any questions before we end for the morning? Okay. All right. Enjoy the beautiful day. See you on Wednesday. Bye all.